So yes, the exam is next week. So the exam covers chapters 4 and 5. So basically quizzes from 5 through 9, I believe, right? So that's what is on the exam. Oh yeah, you can. I'm pretty sure you can. The way to see, have you tried the gradebook in My Math Lab? The way you can review everything that you've done in My Math Lab. Your quizzes, everything really. Let me see. So just go to your gradebook. Now I don't have much in my gradebook. So let's see. Past math entire course. So I only attempted these 2 assignments. So you can just click review. Well, you can do, I don't know if you can do it on the quizzes, but you can always do the study plan. And the study plan is broken down by chapters. And it's like this little symbol. That means I need to practice some of that. So like when you actually open up, let's say chapter 4, it will actually tell you what kind of problems you need to play with. So like for me, it doesn't have anything, but like you would have that little symbol next to basically every problem that you need practice with. So yeah, that study plan is, and that thing, the My Math Lab updates the study plan for you specifically, as I said on. Okay, so yeah, you use that for extra practice. Okay? It's a very nice little tool. But now we're just going to finish chapter 5. So section 5.6 is dealing with exponential models. And we're really only going to focus on 2 of them. The exponential growth model and exponential decay model. Now, the exponential growth model is already given to you. When we talked about the continuous interest rate, the PERT formula, that's the exponential growth model. Now, your book puts it in a slightly different notation just to generalize it. The book uses this form, P of t equals P naught e to the power k t, where k is greater than 0. So book mostly use this for population. They're using P for population. So P of t is population at time t. P naught is initial population. Or at time, population at time 0. So t equals 0, and k is the rate. Yeah, so P is what you start with. Whatever the starting point is. So when t equals 0 doesn't mean, zero split between AC and or whatever AD thing. I can make time equals 0 right now and then see what happens in the future. So whatever you pick for the 0 time is up to you. Now, do you notice how this is no different than the PERT formula? When I gave you the PERT formula, you still have the initial amount, e to the power RT, R is the rate. So, different letters, still the same meaning. Okay, so we use that for exponential growth. Now, the exponential decay is the same exact formula, only you have a negative exponent. So k would still be positive to begin with, but the negative sign will make it all go down. Yeah, k is the rate. So graphically speaking, the growth models look like that, where the y-intercept would be the initial population. So this is the growth model. Decay model, well, is the flipped version of that same graph. The y-intercept is still the initial population, and this is the decay model. And again, it doesn't have to be population. It's whatever amount you start with. Could be money, literally population, could be amount of some material, and so forth and so forth. Anything that has an exponential kind of rate of change, the continuous rate of change. Yeah, p of 0. So, because again, if you put 0 for t, e to the power 0 is 1, so 1 times p naught is p naught. So it's not 1. It's whatever the initial position, initial population is. So that would be the y-intercept. Is that okay? So that's, again, we've played with that model a little bit when we did the money examples, the interest examples. Well, yeah, yeah, you're right. I mean, but we can make predictions for what happened in the past. Like you see, I can say that, no, but what you're thinking about is the time. Like, the fact that k is positive does not affect the location on the horizontal axis. Horizontal axis is the t-axis. Now, if you can allow negative time, because see if I can tell you, like, population of our class was, 28 students with clearly a decay model, right? And we can figure out the rate of decay in population of our class, and we can actually predict what happens on the final. How many people? Anyways. And the y-axis would be the p of t, right? But if I tell you that, the U.S. population now is this, and the rate of, the growth rate is that, I can actually use that model to check, well, what was the population 10 years ago? So I can rewind time and find some points in the past. That's kind of, I think, which maybe not. Is that what you were kind of asking? Yeah, I think you just confused the k and the t. The t is the horizontal axis. So anyways, I'm just going to do a bunch of examples using these models. So here's a fun one. I'm just going to take them out of your book. The rabbit population model. It's always fun to play with rabbits. So let's see. So I'm going to copy that problem. I'll take the picture with me. All right. So under ideal conditions, the population of rabbits has an exponential growth rate of 11.7% per day. which is insane. Okay? And they give us the initial population of rabbits. We start with 100 rabbits. Okay? Now, here's an example that time does not have to be measured in years. Whatever the rate is defined in terms of, in this case it's per day, so we're going to use our time measured per day. With the money, we usually had the annual interest rate, so T was measured in years. We can do an example that say, the monthly rate is this, so time would be measured in months. So usually the measure of time is given in the problem. So part A was just to find the exponential growth function. So really all we need is the initial population and the rate. That's all we need for our exponential growth model, right? And both are given. The initial population is given and the rate is given. So to answer question A, so the population of rabbits at time t, where t would be in days, is starting population, so it's 100, e, to the power of the rate, so it's 0.117 t, where t is measured per day. So on day 0, right now, if I plug in 0 for t, I'll get 100, which is the initial population. Now the whole graph the function, you can use your calculator, but it's just going to look exactly like that. It'll intersect the y-axis at 100. It'll be a little flatter, but it will look like this. Okay?
So,
go ahead. It's it's 0.117. It's converting 11.7 into decimal. All right, so question C. What will the population be after 7 days? So t equals 7. Okay? So for B, if t equals 7, all I have to do is just to plug that in. So P of 7 equals 100 e to the power 0.117 times 7. And I can easily plug this in my calculator. Since my calculator has the e button, so 0.117 times 7, so that's the exponent. I'm going to raise e to that power times 100, so 226, right? And usually the rounding part is kind of tricky here, because by all the rules of rounding, I should say 227, right? But logically speaking, in this case, I shouldn't be rounding up. I'm going to have 226 whole bunnies. 0.8 bunnies will not round up to a whole bunny. Does that make sense? But be careful, like on my math lab, they'll tell you, sometimes they'll just say, just round it up, just mathematically speaking, because a lot of times we're talking not just 226 bunnies, it could be 226.8 million, so, rounding, the decimal happens far, far down the road. So make sure you're really paying attention to the guidelines. Okay? Pretty simple. How about 2 weeks? What do I plug in? 14. So 2 weeks, t equals 14. So it's 100 e, 0.117 times 14. So I'll do the same computation. 0.117 times 14 equals that. Raise e to that power. So 514. Okay. How's that? Actually, just just want to bring this up. The way this model works, again, you can define your initial time, anything you like. I can actually take this point right here as my initial time. Let's say 226 is my initial population. So if I want to do the second part, the 2 weeks from whatever was given, so it's really 7 days from the previous case. Do you agree with that? So I can actually start with 226 as my initial population, and then let t equal 7, because it's 7 days from that point. I'll still arrive at 514. So that model is pretty unique for any 2 points. Does that make sense? Okay. Part D. Find the doubling time. All right, so what that means, in other words, how long does it take for the population of rabbits to double? So how long it takes to go from 100 to 200? How long it takes to go from 1 bunny to 2 bunnies? Right? So I can actually set it up like that, okay? If I go back to the initial population as was given, I want my future population to be 200. I want it to double, right? So all I have to do is to solve for t. So that will answer the question how long it takes to go from 100 to 200, or the doubling time. Are you okay with me setting up this? And really, in this case, the initial population doesn't matter at all. I can say 50 to 100, 17 to 34, it just doubles, okay? Because again, in order for me to solve for t, the first step would be to divide both sides by 100, right? That's the first thing that I'm going to do. So regardless of what initial population is, my equation will be that. 2 equals e2 rate times t. Now, how do we solve this equation when it already has e in it?
Natural log.
Yeah, take natural log of both sides. Is that what you were trying to say? Okay.
So that's always the formula for finding the double.
Well, we're actually going to derive something that you can either go through this process, or your book actually gives you the formula to find the doubling time, which we're about to come up with. It's always going to be the same. But yeah, we're deriving that formula. At this point, we're going to take ln of both sides. So we're going to have natural log of 2 equals, when you take natural log of e to the blah, you're just going to end up with a blah. So the other side is 0.117t. Okay? Are you okay with that? So t then equals ln of 2 over 0.117. So that will tell me how long it takes for the population to double. So natural log of 2 divided by 0.117, so almost 6 days, so 5.9 days or so. Okay. That, what? It's a good business model right there, right? Well, they usually give some kind of a citation where the data comes from. This one doesn't have anything, so it could be just made up. But in general, notice what happens here. When we're talking about the doubling time, 0.117 is our rate. So in general, when talking doubling time, no matter what the numbers are, we will arrive at the point natural log of 2 equals kt. Your book uses capital T for doubling time. Whatever, but yeah, they like to interchange variables here and there, but it doesn't matter. It's same, So from here, you can solve for the rate, k equals ln of 2 over doubling time. If I tell you the doubling time of the rabbit population of whatever, you can find the rate at which the increase happens just by using that formula. Given the doubling time, natural log of 2 dividing by doubling time equals the rate. Or you can solve for the doubling time, which is natural log of 2 over k. And this is what we just did, right? Natural log of 2 over whatever the rate is gave us the time it takes the population to double. So I really don't know if you need to memorize these formulas, because you can very easily derive them if you just understand for something to double, that means you're going to arrive at this equation. 2 times e to whatever, and then you just solve for k, or you solve for t, it doesn't matter. Yeah, it's always going to be like that, because no matter what your initial population is, the double of your initial population, well, it's double of your initial population, right? You start with p naught, you're going to end up with 2 times p naught, right? Double that. So when you start solving that, the first step would be to divide by the initial population. So you're going to arrive at the point e equals e to the power kt. And you start solving that equation, you're going to take natural log of both sides, you're going to get this part right here. And then you just rearrange them any way you like. So you can memorize this, or it's very easy to derive. It takes less than a minute to come up with these formulas. Okay? Well, I'll ask you how long it takes for something to double. But I can ask you how long does it take for something to triple. So you put 3 instead of 2, and I can say, how long does it take for something to, quadruple or increase tenfolds. So it's going to end up with natural log of 10 throughout all of that. Okay? So initial population really doesn't matter when you ask how long does it take for something to double. That means 1 has to turn into 2. If I ask you how long does it take for something to triple, 1 has to turn into 3. And then you natural log both sides, you're going to end up with ln of 3. Is that okay? All right, so let's try this problem. I want to do question, what was a question I wanted to do? Question 8, so that's dealing with money. Okay, so there's a little table there. Okay, so this is the compound, interest compounded continuously, so that's the same model. That's our PERT formula, or again, this is the whole P of t equals P naught e to the kt. So we just have to fill in the blanks. So for part A, they give us the initial amount and they give us the rate. Okay? So we need to find the doubling time and we need to find amount of 5 years. Okay? So to find the doubling time, we can just use that little formula. T equals ln of 2 over k that we just derived. Right? So in this case, for part A, it would be ln of 2 over 0.032. So we will know how long it takes for the amount to double given that rate. The initial amount, again, doesn't matter. $1 has to turn into $2. So natural log of 2 divided by 0.032. So about 21.6 years or so. Okay? Is that right? Are you able to plug that all in your calculator? Years. Now, amount after 5 years, well, our model right now is 35,000 e to the power 0.03232t. So the question is, what is the amount after 5 years? So it's P of 5. So it's 35,000 e to the power 0.032 times 5. And that will tell me how much money we'll have in our account after 5 years. Plug that in the calculator. 0.032 times 5 equals that. Raise e to that power times 35,000. So 4172.88. How's that? Part A was pretty straightforward, right? Okay. Well, part B is a whole lot trickier, because part B would not know the rate, right? We don't know the rate, but we know the initial amount, and we know the amount after 5 years. We know that, okay? So again, for part B, we're starting with this model. This model stays the same, okay? So what is given to us, the initial is 5,000, and P of 5 is 7130.9. Right? So I can actually set this up. I can plug in 7,130.9 in for P of 5 equals 5,000 e to the power k. K is unknown. T in this case would be 5 because we know P of 5, so times 5. So I just have to solve for k. Okay? Does that make sense how we set that up? Yes. So how would we go about solving for k? Well, because it's 5 years. All right, so the first step is to divide both sides by 5,000. So we have 7130.9 over 5,000. I don't have to figure out what it is equals to yet. Equals e to the power k5. Now what? Take the natural log of both sides. So take ln. So that'll give you a natural log of 7130.9 over 5,000 equals just, well, 5k, really, right? When you take natural log of both sides. So to solve for k, divide by 5. So k equals natural log of all that divided by 5. So I can plug that into my calculator. So 7130.9 divided by 5,000 equals that, natural log of that, and divide by 5. So 0.070999. So it looks like 7.1%. So 0.071. Or 7.1%. Is that okay? Hmm? Mm-hmm. That was the last thing that I did here. So if I go back, this was natural log of whatever's in the parentheses, right? So I can go all the way back. So this was 7130 divided by 5,000. So if I multiply this by 5,000, I should get 7130.9. All right, so now we know the rate, 7.1%. Now we can find the doubling time. It's natural log of 2 divided by the rate. Okay, so if you have that formula, it's really fast to use. The doubling time is natural log of 2 over rate. So that's natural log of 2 over 0.071. Okay? So natural log of 2 divided by 0.071, 9.76 years. I'm only going to do A, B, and C because D, E, and F are the same as far as what's missing. But how's that? Does that make sense? But again, the key here is to start with the model and then plug in everything that's given and then see what you can find. Okay? So on part C, we know the rate. We know the amount after 5 years. We don't know the initial amount, right? We can find the doubling time really fast because we know the rate. Because again, the doubling time is irrelevant. No, not that what I was trying to say. What am I trying to say?
Initial time.
Yeah, initial time is irrelevant as far as no, that's a bad word. Well, there's a better word. The doubling time is independent of the initial amount. Yeah, that's nice. I like that. Which is a mathematical term, by the way, the whole independence thing. But the change in initial amount does not affect the doubling time. So doubling time is independent of initial amount. Hey, nice. So C, so the rate was 5.6%. That's given. So right away we can find the doubling time. No problems there. The doubling time is natural log of 2 over K, so that's natural log of 2 over 0.056. I can plug that in my calculator. So 12.38 years or whatever. Okay? So that was nice and simple. Okay. Now, but also need to find the initial population. So this is where this point right here comes in. We know the population at time 5, when t equals 5, and we do know the rate. Right? The only thing that's unknown is the initial population. So let's do that. So again, this is the same model. P of t equals P naught e to the power kt. Now, k is 0.056. That was given to us. And also what's given to us is P of 5, which was 992,347. Right? So again, that implies that t equals 5, because it's P of 5, time equals 5. So if I plug everything into my formula, 9,923.47 equals the initial times e to the power 0.056 times 5. So the unknown is p. Right? Well, that's a linear equation, isn't it? Because this whole thing right here, e to the constant power is a constant. So that's a big constant. So it's a variable times a constant equals some other constant. So how do you solve for the variable? Yeah, divide by the constant. So P naught equals 9,923.47 divided by e to the power 0.056 times 5. Right, that's just a linear equation. So I can plug that in my calculator. My calculator is very crappy, so I have to go backwards. For your fancy graphing calculators, you can just type it in as it appears. But I'll have to start with an exponent. That's the exponent. Then raise e to that power. then flip that, put it in the denominator, and then times 9923.47. So that was, so 7,500 looks like, because of the rounding. Okay? So 7,500 is the initial amount. Okay. Now, D, E, and F, again, they're the same as A, B, and C, just different numbers. So any questions on how we did that? How we were manipulating? Well, yeah, you have plenty of chances. But yeah, you're right. You just have to practice. But again, you're just playing with the same formula. That's the nice thing about it. It's the same formula, you're just playing with that.
Are we gonna get a study guide
Uh, maybe. I don't know. So let me do this example. I'm just going to make something up. Let's say, which population should we play with? This class? How about this class? So, MAT 121 section, what section are you? 3? You're section 3. SBO3. So it does not relate to the online folks. So our initial population was, well, we had a full class, 25, with about, what was the wait list? 3 or 4. So let's just say 29. Should we say 29? No, we'll say 20. Let's just do 27, just to be safe. So initial population of this class is 27. I'm just going to assume whoever showed up today is the population today. I know there are a few people who usually show up, but so that's what? 7? You got to count Shaq? Well, if I count Shaq, then I need to count, then I know that, well, our class size is probably 19 right now. That's who's still registered. Okay? All right, so let's do P of, this is week 12, so let's do P of 12 is 19. Okay? So how many people show up for the final? Yeah, you're looking at them, right? Show up for the final. So final, that means T equals 16, the 16th week, right? So I want to find P of 16, right? Now the initial population was 27, right? And it's E. Now, is this a growth or decay model, first of all? Decay, right? So it's negative. Do I know the rate? No, I don't know the rate. So it's K times 16, right? So I'll have to find the rate first. Do you agree with that? So this is similar to question B. I know initial population, I know population at some point, right? So I'm going to have to use these two facts to find K. So first, find K. But we know that P of 12 is 19, right? So we can set it up as 19 equals 27e to the negative k times 12. Well, that's right now. What? Yeah, population at week 12, which is right now.
So what are we doing with the others?
Well, we have to find that, but I have a problem because I don't know k, right? I cannot just compute that. I need to find k first. So how would you solve for k here? Yeah, divide by 27. But again, 19 is a very optimistic figure. Just because a person on the roster is a little shaky. So 19/27 equals e to the negative k times 12, right? Take natural log of both sides. So it's natural log of 19/27 equals negative 12 times k. So therefore, k equals ln of 19/27 divided by negative 12. Is that okay?
You get that. Why is it? How do you move the negative k to
Well, it's negative k times 12, or it's negative 12 times k. It's a product, right? This is just product, so it's negative k times 12 is negative 12k. You had a question?
To solve that ln of 19/27, you can do it two ways, right?
Yeah, you can do ln of 19 minus ln of 27. But it's easier to go 19/27 and then take the natural log, right? But you're right, if I just go ln of 19 minus ln of 27, I get the same exact thing. Divide by negative 12. Negative 12. So about 3% decay rate per week. Okay? So our weekly decay is 0.3 or 3%. Okay? So therefore, I can go ahead and predict the population on the final. So P of 16 now is 27e to the negative 0.03 times 16. So I have to find the rate first. Okay? So now when I plug everything in, 0.03 times 16 negative raise e to that power times 27. So 16, right? Again, I cannot say it's 16.7. Doesn't make sense. So 16. But again, we have to be really careful with these models in real life when we make predictions, because we know this is we're probably off here. Few reasons. The value of 19 is a little shaky. Just because I have 19 students on the roster does not mean we actually have 19 active students. And the second big issue here is that we haven't passed the withdrawal date yet, right? To assess our true population, the day after the withdrawal date would be a much better number. Then we'll know we'll probably have only 12 students, so that's has it deep in our predictions. Is that okay? By the way, the withdrawal date is what, this week? Sunday, something like that? Okay. So in my list of problems that I wanted to do, I also have number 9. Okay, we're not ready for number 9 yet. That's carbon dating problem. So we can talk about that. Yeah, okay. So this is a decay example. Is that okay? Now, when we're talking about decay, this notion of half-life comes in. Have you heard that term, half-life? This is the same as doubling time, only the other way around. How long it takes to something to half, decrease by half. Okay? So what that means, if I tell you that, I have a pile of something, so here's a pile, and the half-life of the material on that pile, let's say, is 5 years, for example. And again, you depending on what pile is made of, the half-life can vary from, fractions of a second to a couple thousand years, depending on what you deal with. But what that means that after 5 years, how much do I have left? Half of it. And after 5 more years, half of that. And after 5 more years, half of that. And after 5 more years, half of that. So theoretically, it never goes away. I'm always going to have just a little bit left, half of it goes away, a little bit left. So it's one of those paradoxes, but yeah, so if they're talking about, half-life of nuclear, the plutonium or whatever, so it does mean, they tell the half-life is 10,000 years. Does that mean it's all gone after 20,000 years? After 20,000 years, you're only going to end up with a quarter of what you started with, because you keep halving it. Yeah, just a little something left, but so that's the idea. Okay? But again, the big thing here, you just have to realize that if half-life is 5 years, it does not mean that you have nothing left after 10 years. You keep halving things, right? So it's half, quarter, eighth, 16th, and so forth. Okay. So now, again, so when we're talking about half-life, we're dealing with decay model. So that's P of t equals P naught e to the negative kt. Okay? So I can derive the similar formulas that we did for doubling time, only for half-life. Okay? So what that means for half-life is that whatever I start with, so let's use again that capital T for half-life, then after that many years, I'm going to end up with half of what I started with. Okay, so instead of doubling like before, I'm dividing it by 2. So again, I want to solve this equation, let's say for t, or just try to solve this. So the first step that we would take is to divide by the initial amount. So again, just like with doubling time, the half-life is independent of the initial amount. It takes same amount of time for 1 pound to get to half a pound as it takes for half a pound to get to a quarter pound. So it doesn't matter what you start with, okay? So to solve this, again, I'm going to have to take natural logs of both sides. So take ln of both sides. So that becomes natural log of 1/2 equals negative k times t. T would be the half-life. So this looks very similar to the doubling formulas that we're playing with. Actually, we can make them look identical, because 1/2 is the same as 2 to the power negative 1. You hear that? Then 1/2 is the same as 2 to the power negative 1, just by the way exponents work. Yeah? Yeah. So by the rules of exponents, what can I do with the negative 1? Sorry, by the rules of logarithms, what can I do with the negative 1? Yeah, bring it down. So it becomes negative 1 times natural log of 2 equals negative kt. Right? So both sides are negative. I can just divide by negative or multiply by negative. The negatives cancel. So that leaves me with natural log of 2 equals kt. So now it's identical to what we had with the doubling time. Well, because we're using slightly different formulas. Our formula has that negative sign in there. So that actually kind of nice. It gives us the same set of formulas that rate equals natural log of 2 over the doubling time, or the doubling time equals natural log of 2 over the rate. So it's the same exact thing. Did I say doubling time? I meant half time. So it's the same exact thing as with the doubling time formulas. Yeah, so it's the same relationship between the rate and the time it takes to double in the growth model. In the growth model, where's the growth model? Well, the growth model, as it's with the decay model. Well, the difference is in the model itself, the negative sign. That's where the difference comes in. But that negative sign allows us to just play with the same formula. So if you know the half-life, you know the rate. Or if you know the rate, you know the half-life. Okay, so let's take a little break, and we'll play with the half-life. Oh yeah, this is easier. Calc is easier than this.
I need to know all this, right?
Yeah. Oh yeah. So let's talk about carbon dating, or so I'm not really, a chemist or biologist or whatever, so I don't know the old fun details of that process, but I understand the math behind it. So apparently there is this thing called carbon-14 that stays constant in a living tissue, whether it's a animal tissue or a tree or whatever, and starts decreasing when the tissue dies, whether it's a flesh or a leaf or a branch or whatever. Well, actually, I think there's, again, don't quote me on that, but there's carbon-14 and carbon-16, and carbon-16 stays constant no matter what, and carbon-14 starts decaying when something dies. So they just look at the ratio of two carbons in the body, and they can predict how long ago the death occurred. So the half-life of carbon-14 is 5750, so 5,750 years. I could be wrong. Yes, that's right, 5750. You don't have to have it memorized by no means. It will be given to you on whatever problem you're working on. So you don't have to actually memorize the half-lives of different chemical or different elements. Okay? But forever, the half-life of carbon-14 is 5750. That's fixed. But if you need it on the test or whatever, that's given to you. You don't have to memorize that. So I just want to do this question when we do carbon dating, the question 9. So let me copy that. It's a funny picture. Well, not funny, but fun picture that comes with it. I think some teeth and jaw, something they found. So there's a story. Come on, scroll down. All right, let's go down. So 1970, somewhere in Indiana, discovered teeth and jaw bones while something. So here's the big thing, that 77.2% of carbon-14 was lost. Okay? So that means 100% became 22.8%. Okay? So that's the level of decay. You lost 77.2%, that means you still have 22.8% left. So how old were the bones when they were discovered? So in 1970. But really, it's what, 40 years from now, it's really relevant in comparison to the half-life of carbon-14. So anyway, so again, so it's a decay model. The model is P of t equals P naught e to the negative kt, right? Now we don't know the rate, and we will be looking for time, right? We're looking for how old that thing really is. So we're looking for time, but first, find rate. Well, that's simple because we know the half-life of carbon-14. So the formula K equals ln of 2 over T, of half-life. So that's going to be a very small number. So it's a natural log of 2 divided by 5750. So, yeah. So how many decimals is that? So it's so it's 0.00000012. I'll just stick with that. Okay. So then, so this is our model now. P of T. Yeah, so that would be the rate of carbon-14 decays at the rate of, which is 0.012%, okay, per year. Yeah, because our half-life was given in years, so everything is going to be in years. Because the half-life could be in seconds, so everything would be in seconds. So then our model is P naught E negative 0.00012 T. Okay. So now we can actually go ahead and figure out how old that thing is. So the thing here, we have to be very careful how we interpret this number. Okay? So 77.2% lost. So that means you started with 100%, right? So that's your initial amount. It's 100. So it's 1. E to the negative 0.00012 T. And you lose 77.2%. So what you have left is 0.228, right? Because you're losing 77.2, so you're left with 22.8%. Okay. So you'll see two types of phrasing. Sometimes they'll say that the amount of carbon-14 that is left is 22%. So you put it on the right. That's what's left. Or they'll say that's how much we lost. So you subtract that from 100, so that's what you have left. So you went from 100% to point. Yeah, so started initial is 100. Okay. So I can go ahead and start taking natural logs of this thing, right? So now I just have to solve for T. So natural log of 0.228 equals negative 0.00012 T. So solving for T gives us natural log of 0.228 over negative 0.00012. So that number will tell us how old that thing is. Nope. 0.228. So 12,320 years. Okay? Pretty old. Okay? Mm-hmm. Well, that kind of makes sense, right? Because we basically have a quarter left, right? So the half-life happened twice, so that's already over 11,000 years, and then some more to get, because it's less than a quarter, right? So it's a little bit more than twice the half-life. Now the carbon dating does not work with, the dinosaurs and stuff, because those are no longer bones. Those are really rocks. When you find the dinosaur bones, those are not bones. They're already fossilized or whatever. So and again, since the measure goes in millions of years, there's virtually none of that carbon. Well, there's no carbon left because it's just. And well, I should take it back. There's carbon left, but there are different ways of dating. You need something with a higher half-life. Okay, but is that all right? So it's very similar to what we did with money with the growth models, only now it's decaying. Is that okay?
I was kind of confused on how you got the rate. This is 1.2 something something on the calculator.
Yeah, but it's 1.2. It's 1.2 with the 4 decimal places moved. That -4 here, that means move the decimal places 4 to the left. Okay, so look what happens if I add 1 to this. I'll get 1, 0, 0, 0, 1, 2. So it's 0.00012. Okay, so you have to pay attention to that scientific thing in your calculator. Okay, so let's try kind of the similar table. Let's try question 11 in your book. So the radioactive decay. So we have a bunch of different elements, and we have the rate and the half-life. So we just have to play between one and the other. So since we derived those little formulas, shouldn't be too bad. Okay. So like for example, we have a polonium-218, whatever that is. We don't need to know what that is. But all they give us that the half-life is 3.1 minutes. Pretty fast. So the rate, the decay rate, would be ln of 2 divided by the half-life, 3.1, right? So if I do that on a calculator, natural log of 2 divided by 3.1, so what, about 22%? But that's per day, right? Because the half-life was measured in days. I'm sorry, not per day, per minute, in minutes. So this is 22.36%. That's the daily rate. What am I doing daily again? Every minute. Oh. Okay, so K is ln of 2 over 3.1, which was 22.36% every minute. So that's the rate per minute. Okay? Yeah. Now for lead, the half-life is 22.3 years. Okay? So we can find the rate by going natural log of 2 divided by 22.3. So whatever that is, that's going to be rate. So about 3.1% annual rate. That's the rate of decay. All right? And so forth. Like if we want to talk about iodine, so that's 1.15 rate of decrease per day. So then the half-life would be natural log of 2 divided by the rate, so it's 0.015. So we can find the half-life of iodine. I did something wrong. Natural log of 2 divided. Yeah, so about 46 days, right? Plutonium is always fun. It's 24,000 years. So we can find the rate by taking natural log of 2, dividing it by 24,100 years. So it's natural log of 2 so that's going to be, again, we have to be careful here, because that's going to give us that scientific notation again. So see, now it's 5 decimals. So it's 0.40 287 or whatever. So it's a very, very small rate. Okay? So it's 0.0000287 or 288. Okay? So that's annual. Now the rate, of course, moved two decimals to the right. This is just a decimal thing to make it percentage. Maybe in those cases it's easier to measure it in millennia. You can say, well, it's 24.1 millennia instead of years. Then you're going to get something a little with a fewer decimal places. Is that okay? So anyway, so the decay model works just like the growth model. You just have a negative in the exponent. So that's about it. Okay, so those are all fun. Now there are multiple different models. I want to do one more example where the model is a little bit different. You don't need to memorize the formula. Usually in those cases the formula is given to you. And if you're working on the homework, you can look it up. But I want to do question 17. So this is going to have a different model from what we've played with so far, but we can still handle it because we know how to solve questions. So I want to do question 17. So here's an epidemic spreading type of model in a small town of 3,500 people. So the model is given to us. Now where the formula comes from is a different story, but here it is. So they gave us the formula. So basically that tells us the n is the number of infected at time t. Okay? When the epidemic began. All right, so grab the function that, you can do it on your calculator. I mean, that would be actually a fun thing to do. Let's see what the graph looks like. So what's our foo plot, our favorite? I don't know. I mean, I have to be careful. So it's 3,500 divided by 1 plus 19.9, was it? Times e to the power negative. Okay, I don't remember. Negative 0.6t. I'll need it. Just in case. Times, well, x, because I think that's good. Well, I have to really be careful with my x's, because the x should go from probably 0 to, I don't know, how about 10? And the y, let's keep y between 0 and 3,500. Here we go. So see what happens? This is your initial number of sick people, and then it's kind of growing, then it's really expedites here, right? If you think about how fast it starts growing, and then it's slowing down because, well, it cannot go past 3,500, right? Does that make sense? Because you only have 3,500 people. If I increase the value on the x, well, see what happens? It basically gets up there and then it just flattens. Well, we don't know whether disease is deadly. Does it say deadly? There's just everybody's sick, right? If I go, look, you see, if I do 3,700 limit on the y-axis, so you see we kind of have an asymptote at 3,500. But we don't quite get there. So that's the graph. Okay? So anyways, well, in the foo plot, t is your independent variable. Now the foo plot is in terms of x, function of x. What?
I don't get what we're doing. It's different.
Well, it's a different model, okay? And it's a right. It's not. It's probably the growth doesn't just happen simply exponentially. Just something else going on here. Because again, we're going to flatten out. We don't have because there is a limit to how far the disease can spread. If we just use the exponential model, then eventually it's going to infinity. This one has to flatten out. Now, so initial infected. So time equals 0. That should be pretty easy to do, right? We just need to compute n of 0. So it's 3,500 over 1 plus 19.9 e to the power 0. And what is e to the power 0? 1. So then it's 19.9 plus 1, so that's 20.9. So it will tell us, so we start with 176, did I say 76? I meant 67. 167 infected people. So the rest, find the model of infected after 8 days, 12 days. You just plug in the numbers, okay? So we can do n of 2, n of 5, n of 8, and n of 12, okay? I'll do n of 2, and you guys pick one, because I don't want to, whoever has a calculator handy. We should lose some people after the break. So who's going to do n of 5? Who's doing n of 5? Okay, you'll do it. Who's going to do n of 8? Sure, Mikey. And n of 12? Anyone? Do you have a calculator? Well, you're going to call somebody? So I'm going to do one. Oh, no. So I'm getting 500. Who was doing n of 5? Yeah. 1,758. Oh, Mike, you don't have a calculator? But doesn't that thing have a calculator? Well, you don't need a smart calculator. You just need a scientific calculator. Did you do 12? Yeah, but if you flip it, yeah. Yeah, just put it on the side. The whole phone. Just it gets scientific, right? Yeah. All right. Well, that's probably not right. Oh, maybe it is right. No. It should never be more than 3,500. It's always going to stay less than 3,500 times 8 equals that much, negative. Raise e to that power times 19.9 equals that plus 1 equals that. Right. Times 3,500. Yeah, so about 3,007. And again, this is just a model. Doesn't mean, we just use it to predict things. So what is it for 12, Lindsay?
I don't know.
Oh.
Still can't figure it
All right. Well, it's time to learn your calculators. You'll need it on your test. And by the way, you cannot use that on your test. You know that, right?
out. Yeah, I have a graph.
Okay. We should be really close to 3,500 after 12 days. So 34.48.
When we're about 16, then would it be like
It'll be, again, it'll probably be very close. But it's slowing down. It will never reach 3,500 using this model. That's what question D is asking. Using this model, you'll never get to 35 exactly, but, if you just think about this, if 3,499 people get sick, then the last guy or girl, realistically speaking, the whole town will get sick. But according to this model, you're still going to get one healthy person left. Or a fraction of that healthy person. Really, that's going to be a fraction of it. You're going to get 3,499 point as many nines as you like. So again, it's just a model. So what, for 16, if we do 16, so 3,495 for 16. But again, see, the thing is, using this model, the answer is no. It will never get to 3,500 exactly using this model. Because again, it's just a model. But it does a pretty good job for the smaller numbers. Okay? But using this model, if again I go back to the graph, if I zoom in here, if I let my y to be between 3,499 and 3,501, I don't know, I can zoom in even further. Well, it seems like it's hitting that, but it won't. I mean, it won't. You're always going to get a small, tiny little gap in there, just the way this function is written. Again, is that a realistic model in the long run? Probably not, but in the short run, it does a decent job, and that's really all that matters here. So the answer is no. Because in order for that to happen, your denominator has to equal 1 exactly, and it never will. Because the way those functions work. But realistically speaking, probably everybody gets sick. Is that okay? Well, so that's about it. That's all there is to it.
give an example of substitution in the mod. If we use
Yeah. Did you look at the notes from last week? So did that one make sense? The one we did in
I
class?
just had trouble when it was you had to solve it. You couldn't just factor it. You just solve it.
Oh, if you can just factor them, just by all means, you can
But
factor.
no, like in the homework you can't factor.
Well, okay. So let's just say you have this one. So let's say it's it's e to the x. I'm just making one up plus 7 So they usually start like that. It's 7e to the negative x minus, I don't know, 1 equals 0. Okay, something like that. All right? So the first thing that we did, we multiplied both sides by e to the x. So that's e to the 2x minus e to the x plus 7, right? When you multiply this, that's e to the x squared, which is same as e to the 2x. You multiply that, that's your negative e to the x. And when you multiply here, e to the x will cancel with e to the negative x. And you're just left with a 7. So this is the case where probably won't factor. Okay, you won't be able to factor that. But again, if I make a substitution, let u equal e to the x, that becomes u squared minus u plus, okay, that's a bad example. That won't work, period. Let me make it minus 7 in the middle. So minus 7. Otherwise, we get imaginary solutions. We don't like that. That won't happen with those problems. If you start getting into imaginary stuff, then just stop, because you don't want to be taking natural logs of imaginary stuff. But anyway, so here it is. Here's an equation. That's a quadratic equation that doesn't factor. So how do you solve a quadratic equation that doesn't factor? Here's a quadratic formula. So u equals 1 plus or minus the square root of 1 minus 4ac over 2a. So it is 1 plus or minus square root of 29 over 2. Right? Okay. So that means when you substitute back, you get e to the x equals 1 plus square root of 29 over 2, or e to the x equals 1 minus square root of 29 over 2. Right? You have two solutions. Now, this one right here is negative. 1 minus square root of 29 is a negative number, right? Now, the range of e to the x is strictly positive. So e to the x cannot equal a negative number. Is that right? So that one has no solutions. This one, just take natural log of both sides. So x equals natural log of 1 plus square root of 29 over 2. That you can just plug in your calculator, right? It's just something ugly, but it's going to be ugly anyways. So 29 square root plus 1 equals that. Divide by 2 equals that. Natural log of that. So 1.16 or so. Okay? So just because it didn't factor doesn't matter. You can still solve it using quadratic. There's a little fly right here. Go away. See that? What? Yeah. So is that okay? I'm glad you watched the recording. I know. That's my point. Exactly. Based on having, 7 people out of 19,
I don't think I finished it.
I'm not getting that many hits on those YouTube videos.
I watched like 15 minutes of it.
Did you watch one from Wednesday, the 30-minute one?
Yeah.
Okay. They were just examples. I did it from home.
Well, a lot of times when I'm watching them, I'll watch like most of it, and I'll be like, okay.
No, it's all right. Okay. Any other questions? Yeah. We're reviewing on Monday. And you will take tests on Wednesday. Online people can take tests whenever they like by the end of next week.